Said, ooh, girl, you shock me like electric eel. Baby girl, you turn me on with your electric feel.
Hello, budding physicists, and welcome back to another round of practice problems. And when I say round, I mean single practice problem. Today, we are going to drive through the essentials of these electromagnetism problems. They focus on drawing all of your forces, just as you did previously in 7a. However, this time around, they are due to electromagnetic interactions. We are going to write down all of those forces. We are going to quantify those forces using Coulomb's law. From there, we are going to do some math and quantify some aspects about the system and wrap it all up back together with a good physical understanding of how these charges are being pushed and pulled around based on where they are with respect to one another. So, to explore that, we are using this lovely imaginative example of a repulsive croquet game, an electromagnetic croquet tournament. Our heroine Jessica hits her positively charged ball, pictured on the right, sending it across the playing field, rolling to the left along the x-axis. It is repelled by two other positive charges. These two equal charges are fixed on the y-axis at the locations shown in the figure. A, we're going to express the force on the ball in terms of the ball's position x. Foremost, the use of position x means that we probably want to draw our coordinate system, which you astute individuals may have remembered previously. We always do. We're back to our real two-dimensional situations where we have to establish coordinate systems and accordingly draw lots of stuff. I'm calling that y, even though it's sort of irrelevant. We're not going to jump off of this axis because the forces in the up and down directions do something special, as we'll see shortly. So this is our initial velocity. We're not going to have to figure out what the velocity is for all space and time because that requires some difficult integration, maybe impossible integration. But those of you that are interested can try that on your own. So as always, we then ask ourselves, what causes the force on the object? What physical sources of force are we looking at? The name of the chapter may have tipped you off that this is a charged up situation. Coulomb's law is going to give us interactions between these charges that, because they are like charges, cause repulsive forces. Those forces are going to act in the direction opposite their distance between them. Drawing the first one, we're going to call this charge 1 and charge 2. We're going to draw F of 1 on 3. So I'm going to label these in gray so it doesn't get too cluttered. We trace out the distance between the two and say, okay, if I follow that line, I get that force. This is F of 1 on 3. And I can do the same, accounting for the F of 2 on 3. F of 2 on 3. Now, what can I say about these two forces in relationship to each other? This is going to be a concept that comes up numerous times in this class. We're going to seek out symmetries in the problem. We're going to seek out ways in which the problem is similar to itself. And doing so allows us to tackle complex, infinite sources of charge with ease, hopefully, or more ease than we would have dealt with previously. I look at these two forces and I say, well, what does Coulomb's law depend on? Coulomb's law, which I'll write for reference up top, tells us that the force between charges 1 and 2, being arbitrary labels, is equal to the product of the two charges themselves times some constant, which is true in this universe, and divided by the distance between those two particles, and divided by the distance between those two charges. And that force points along r, where r is the distance between the two charges. Q1, Q2. Which is all a little mathy looking, but basically all it's saying is that there's some scale, k, that's well and good. With a larger charge, we get a bigger force. With two larger charges, we get an even bigger force. And with a larger distance, we get a progressively smaller force. It scales with 1 over r squared. As we experience in real life, the further two charged things get away from each other, the less they attract or repel. And the more stuff, the more grist of charge, its innards, its essence. Just like the essence of Santa Cruz is surf and sun, just like the essence of physics is fun with the pH, our charges themselves are the essence of these forces. They're some unknowable object that we can only see via how they create forces, how they create these Coulomb forces. And we then ask, based on the geometry of this problem, how do these two forces compare to one another? Are Q1 and Q2 the same in magnitude? The answer is yes, therefore their product with charge 3 will also be the same. So, cool, the sizes of the charges are the same, that's one symmetric thing. Are the distances the same? Also yes, we're dealing with charges that are equidistant from the axis on which charge 3 is traveling. We know this will be true for any x position of our charge 3. The way I've drawn these forces is accurate in that they both have the same magnitude. They're both pointing up the same angle from the x-axis. Now, with that information, I can go to the next step of my free body diagram. Believe it or not, we've been drawing a free body diagram, your favorite. The next step being figure out what our net forces should be. So I'll rewrite this. And I want to draw in my net force without doing any math first. So our x components appear to add to one another. And because they're the same, we can say that our net force in the x direction is going to be twice the length of those vectors. Now, is there any net force in the y direction? Well, because the y components of each individual vector cancel each other out, they're the same size in opposite directions, then we will have no component of our net force in the y direction. So our net force is going to be equal to twice times the x component of, we'll say, 1 on 3, x. So what is our x component of f of 1 on 3? Now we have to look at our whole geometry and do a little thinking. What I need to get that component, thinking back, is that I have some sort of triangle that I can make with the x-axis, and that triangle contains an angle theta that I can use to project the total magnitude onto the x-axis, knowing that the x-axis is the adjacent side, and say that this is f of 1 on 3 total magnitude times cosine of theta. So what is cosine of theta? Looking at our bigger geometry, let's fill in some of the blanks. So I'm going to label an existing triangle that I know a lot about. I see, well, okay, this triangle by itself I might not know too much about, but if I look at what I have labeled immediately, I have a b from this distance from the axis, and I have an x, which is the distance to the charge, and I will use that to make a triangle. Now, if I want to know that angle down there, I ask myself, how can I relate it to this triangle I've drawn up here? if this triangle was slightly more skillfully constructed, I would see that this line that runs through the charge is the same line that this vector shares, and they both share this other line, the horizontal axis, the x-axis, meaning that these two angles, the theta that I talked about previously, and this angle that I can connect to b and x are in fact the same angle. They are a vertical angle, and this is a right triangle. Now I connect this theta with b and x. I say that foremost, I want the cosine of this angle. Now, if you were given this with numbers, there'd be an easy way to do this. You just go ahead and do your trig ratio with your existing numbers, but we want to do a little trick because we're doing this problem algebraically first. This is something that's useful to do to practice your algebra and solidify your understanding of the problem. So I'm going to show you guys a trick that we can do. We know that we want the cosine, as we stated down here. So I ask myself, well, I want a cosine, so I want an adjacent side and a hypotenuse. So looking at this triangle, which shares this theta, how do I find an adjacent side and a hypotenuse? Well, this is a nice adjacent side, but our hypotenuse is, as of currently, unknown. So how do we figure out the third side on a right triangle? You know this very well to be a dear friend, Pythagorean theorem, which I have glossed over a step of, but if this side is c, c squared is equal to its two legs added up and squared, giving this square root form. That is going to tell us something next. Moving down here to avoid clutter. From the b comma x triangle, we know that cosine of theta is going to be equal to the adjacent side, which is x, divided by the square root of b squared plus x squared. This is where the math gets a little weird looking, but we accept that because we are pioneers of the unknown, and no amount of weirdness will deter us from what is truly out there. That's what I tell myself whenever I start watching a new anime, by the way, as a pep talk. So we dive into this weirdness, and we've got our cosine. Now, moving back to here, I'm going to start writing things out linearly. We know that our f net is equal to 2 times f of 1 on 3, comma x. We figured out that f of 1 on 3, comma x is equal to f of 1 on 3 cosine theta. I did that all pictorially. So our f net is going to look like 2 times f of 1 on 3 cosine theta. And further, we know that cosine theta is this fun algebraic mess. A fun mess, just like my 21st birthday party. I'm just kidding. I didn't actually do anything fun on my 21st birthday party. So we've got this information, which, spoiler alert, we haven't done any electromagnetism yet. We've just wrote down some angles and stuff we knew from our last class. But now we're going to get into the meaty bits. The f of 1 on 3, which we get from what physical law? How do we know how these charges actually interact? Well, this is a Coulomb's law. Exclamation mark. We know that this is just going to be what we wrote up there. Q1, Q3, and R 1, 3 squared. And this is getting a little daunting looking, but again, you guys have strong constitutions, and I believe in your ability to get through this. Can we write down anything else about this? Is any term in here, K, Q1, Q3, R13, are any of those terms representable in terms of other things we know? Let's look at our picture again. So our Q's are just Q's. Those are some sort of constants in the problem. Our R, though, we've actually already written down in terms of other things. I'll give you a second to look at that and say, yes, my distance between charge 1 and 3 is actually the hypotenuse of this triangle. I'm going to succeed, and I'm going to write that I know that. Whoop. Equals b squared plus x squared. Square root. And we plug that in, noticing that we have a square of a square root conveniently, canceling that square root. And now we're pretty much done writing down that net force. The outstanding question is, can we write it down any simpler, any more can we write this down any more simply? I say yes. We have this thing, b squared plus x squared, that shows up in two places, and I'm going to remind us that b squared plus x squared all square rooted can be written like that, and we're multiplying it by this thing. So no matter what our guts are in here, if you're multiplying two things that have the same base but a different exponent, then you add the exponent. So I write that as the next step, that we now collect our numerators, and we write that. We now have a term for our F net. Beautiful. And what direction is this force pointing? As we drew, it's pointing to the right, along the positive x direction. Give it some electrocution effects for beauty. Lovely. I've never seen physics this beautiful. Let's think about this math for a second. This is a little bit of a weird looking math equation, and normally you could just leave this and say this is fine, but I want to go one step further and show you guys what this equation actually looks like. So you could either use a knowledge of functions or just plug in the basic form of this into Google. And when I say basic form, I mean, let's turn all of the parameters that we don't care about into ones, because like there's some value and they're not going to change what the function looks like. They're just going to change how stretched it is. Our function looks like f of x is equal to 2x over 1 plus x squared all to the 3/2. Plug this into Google, or combine these two functions to draw that this is going to look like this. This part is positive, and it sort of increases to a maximum of some sort. And then this part is negative, and it also increases to a maximum. Okay, based on this picture, how do I interpret the force? How do I think of this object moving along the number line and saying, I'm feeling a force, I'm feeling a force. Oh, it's a little weaker, it's a little stronger. How do I interpret all of that? So I go down to here and I ask, first off, what's my direction? If my peak is positive right here, what does that mean? Because this is to the right, positive means that we're pushing right on the charge, and pushing left for the negative. So our charge is going to be repelled to the right or to the left, depending on whether it's on the right side or the left side. Well, that's kind of silly. Like, if you know that these charges repel each other, you could have told me that without doing any of that math. You could have said this positive charge is just going to shoot out to the right because there are other positive charges that it's avoiding. This charge just walked into Whole Foods and saw its X and was like, I don't really need that asparagus water. I'm out of here. And similarly, it can go to the left and also get ejected from New Leaf when it sees its other X and doesn't want anything to do with that. I'm just kidding. People can have positive relationships with people they've dated before. So it goes to the right, it goes to the left, it goes to 0 in the middle. It has these maximum pushing points, which seem a little interesting to me. I kind of like that idea of like, this is the strongest place it's going to push. And we say, okay, that matches with our intuition. We kind of figured out something new and that there's a maximum pushing point, maximum force point. And we say, all right, that's mathy and gross, but I kind of got a feel for it. And now I'm going to move on with my life. So we do just that. We move on to part B. At what value of X is the deceleration maximum? Oh, dang. Well, if we're talking about deceleration, what are we talking about in terms of our forces? We can connect force and acceleration. And mind you, this deceleration, I probably would not have jived with if I wrote this problem. I would have just said, like, acceleration's magnitude. It's just the place where it's slowing down the quickest, but if it's just going to the right, that's just saying where the acceleration is strongest on it. So where the acceleration is strongest is where the force is strongest. We know because of our dear friend, Newton's second law, near and dear to our hearts. And we then say, okay, this is actually a question about force. Where is F a maximum? Question mark. Well, because we did that little bonus exploration, we saw that there is a maximum and it's somewhere over here. We don't know exactly where that maximum is, but we know how to find it. Do we know how to find it? Of course, we just look at the graph. No, we have sophisticated mechanisms. What we're going to do is see this is a function of x. And a function of x has a maximum where its blank is equal to 0. That's right, you guessed it, it's derivative. So we've got this gross thing to take a derivative of. Congratulations, everyone. Congratulations. So I'm going to rewrite this. So we want to figure out where that is a maximum. So again, we have to kind of like ignore that garbage with the K and the Q and the Q and the B, but we're not going to write them as ones this time. We're just going to let them be the constants that they are. Okay, we're going to break this down. It's got two parts that have x's in it. So if we're going to do the derivative with respect to x, we've got to see, all right, how am I going to combine my derivative of x and how am I going to combine my derivative of this bottom stuff? You could, recognizing that it's a quotient, do a quotient rule, but I am personally not super inclined to a quotient rule. So what I'm going to look at this and say is that I've got two functions. I've got an f of x and a g of x that are being multiplied together, where f of x is my x times all my constant garbage, and g of x is going to be 1 over this bottom term. So what I'm going to do here is I'm going to say that if I take the derivative of this, I can use my product rule to write the derivative of each term multiplied with the not derivative of the other term, as we've done many times in our math experiences. My derivative of my f of x, which is garbage times x, is just garbage. It's all just garbage when you get down to it. And okay, I'll write the garbage to make life look a little better. And my g prime of x is a little more daunting. So this is a term that we can write a little differently. If we're going to take the derivative of something with a power, we want to write it in terms of just the power. That means I'm going to write it just negative 3/2. I'm not going to have the divided by or anything, because I know that this is just one thing. It's an exponent. It's this inside stuff to the negative 3/2. So my outside derivative is just something to the negative 3/2, which allows me to do a power rule and say I multiply the front by the power, I leave the insides the same, and I subtract 1 from the power. From here, I go ahead and continue to the chain rule. I have this inside term with a b squared and an x squared, and I'm going to take that derivative. Our b squared's derivative is just 0 because it's a constant, and our x squared's derivative is going to be another power rule, 2 times x. So combining this a little bit nicelier, a little bit more gooder, a little bit more purty, it's my result. There we go. We now have our two terms. We have our f prime of x and our g prime of x. Let's move forward. This problem's a little harder than I thought it would be, but we can do it. If you guys can follow along with this one, you can tackle any of the other problems, no sweat. And maybe you could have done that already. You don't need me. No one really needs me. Except for a plant that I bought the other day. Maybe just for the sole purpose of being needed. Is that why we have pets? Is that why we nurture to be needed? Questions unanswerable by physics. So I'm going to combine this nice quotient rule instead. I have my f prime of x, which is this, 2 times k times q1, q3. Then my g of x, which is just b squared plus x squared all to the 3/2, negative. Then my f of x, originally garbage, times x multiplied by my g prime of x, which is this value. So in total, I have kind of a mess, but it's a correct mess. A mess made of garbage and correctness. Next up, I can simplify by reminding myself that I'm setting this all equal to 0. So 0 is equal to this stuff, which I'm going to rewrite, and it's going to look the same. How do I simplify this problem? I love that 0. I know that it can do great things for me if I factor out some constants and divide by them. So I try to note every single thing that's the same in each of these two terms. I see that the 2 is the same, the k is the same, the q is the same. Stop me if this is getting obvious. What's going to happen here? I'm going to make a little assertion that I can divide by this 3/2 because my b squared plus x squared to the negative 5/2 actually has a b squared plus x squared to the negative 3/2 hidden inside of it. Okay, so what did I mean when I say that negative 5/2 has a negative 3/2 in it? I'm going to break this down a couple ways because this is an important concept to get mathematically. So if I have a to the negative 7/2, for example, and I want to break this down into a factor that has negative 3/2, what I can do is say it's a to the negative 3/2 times something else. And this something else is what I can add up with 3/2 to get 7/2 fractions. But really, I'm just adding up 3 and 7 because the denominators are going to be the same. So 3 plus something gets me 7. That something is 4. So I do that. Negative 4. I do that, and that allows me to factor that out and write my 7/2 in terms of this, which turns out to simplify to negative 2. So I factored out a to the negative 2 and a to the 3/2. That's the forward way of doing it. The backwards way of doing it is just dividing and hoping things work out, which is what we did. So I do that, and I say, in this situation, I'm dividing by exponents with the same base, so I take their exponents and I subtract them. I'm going to do negative 5/2 minus negative 3/2, which becomes a positive and allows me to add this, giving me a much nicer term. This turns out to be negative 2/2, which is equal to 1. So I get that this is b squared plus x squared to the 1 power. Neato burrito. Now, all I have to do is solve for x. Again, I continue to simplify. Guessing you guys are probably bored of math by now, but I never tire. I am an infinite math machine. So I've rewritten that to be on the bottom. I now say, oh, well, I guess I probably should have multiplied by something else because these fractions have different bases and I don't like that. So I'm just going to get rid of this base by multiplying everything by that factor. Bloop. And I can do that on both sides because 0 eats that multiplication again. So 1 times b squared plus x squared is just b squared plus x squared, now subtracted by 3/2 x. Oh boy, we're almost there. It's so close, so deliciously close. Holy cow. Multiply both sides. Oh my goodness, I'm just gonna dance in jubilation. Wow. Plus or minus. So I did a square root in there. Gotta remember your plus or minuses, otherwise the tooth fairy will come back and steal all of your adult teeth. And there you have it. It's an answer for maximum values or minimum values. Now, a thorough mathematician, which we are not, would plug that back into the equation and figure out if it's a maximum or a minimum. Forget that, because we already know what this function looks like. So keep this in mind, plus or minus b times the square root of 2. Square root of 2 just means some rando number. Go back up, and we say, okay, that it probably corresponds to something I've already seen. It's these two bumps. It's my either b times square root of 2 or negative b times square root of 2. Beautiful features of this graph. Now, that agrees perfectly with our picture. That agrees well with the physics. The math and physics all mesh together into a harmonious picture, and we can ask more questions of it. Like, granted, we've already answered the question. This is the max acceleration. But there's so much more. We say, well, what if b changes? If b gets bigger, then this point gets pushed further out. And if b gets smaller, it gets pushed further in. So if we look at this scenario, what that's saying is that the range of the strength of this acceleration depends on how close in these charges are. If they're really close, then there's a spike super close in here. We'll just draw a quick little spike. If they're really close, then there's like a spike and then it goes off to nothing. But if they're really far apart, then it's a gradual spike and then it goes to nothing. So the features of this croquet course can be scaled as you change B. This can be some sort of device that you're making in the lab where you want to scale a force. This could be a biological process where the proximity of ions interacting with one another deliver different effects based on their spacing. It could be any number of things, and yet it came from such a simple little drawing of 3 charges and ate away hours of our life. But hey, that's physics for you. So to recap, in this problem, we very carefully drew all of our triangles. We said we're going to be dealing with Coulomb's law, so we know that our F2 on 3 and F1 on 3 are symmetric. They're just mirror images over this axis, and their y components cancel out, so we just get an x component in this direction. We fiddle around with the geometry, figuring out that our cosine of theta can be related to our b squared and our x squared, giving us our total F net. And from that, we do some algebra. We include Coulomb's law for the magnitude of these forces and combine it all mathematically to this form. We explored that form using a graphing utility or our graphing intuition and discovered, ooh, this thing looks like it has some maximum values. This thing is pushing to the right and to the left, but stronger and weaker in different places. And then we figured out where those points are by simply taking a derivative. And when I say simply, I mean it took a little bit of math, but hey, we got a value. It's clean, it's believable, it's delicious. I will eat nothing but this value for the rest of my life. I am satisfied. So thank you for slogging through this with me. There are a lot of essential points made here about concepts that you'll see in other problems, all kind of conglomerated together in one big slog. So if there are specific things about specific problems that you want to see in a more isolated format, please ask me about that and I can see what I will do. So enjoy your lives, stay charged up, and farewell.